Today we're going to be looking at limit rules and how to calculate some basic limits. So far we've been using tables of values or graphs to approximate our limits, but those aren't very exact methods. So today we're going to learn some more algebraic ways to calculate limits. First, let's look at the function y equals a, where a is a constant. So the graph of this is just a horizontal line. If we try and find the limit as x approaches c, where c is just some x value, as my x's get closer and closer to c, the y values will get closer and closer to a because they're always a. So we can see here that the limit as x approaches c of just a constant a is just that constant a. Now let's look at the function y equals x. Again, I'm just going to take an arbitrary value, x equals c, and then I want to know, as my x's get closer and closer to c, what do my y values approach? But since my function is y equals x, the y values will also approach the value of c. So we see here that as I take the limit as x approaches c of the function x, I will get the limit of c. Let's try a couple of examples applying these theorems. So first, let's take the limit as x approaches 2 of the function 5. Well, since 5 is a constant, no matter what x value I'm taking the limit at, this limit is going to equal 5. Let's try the limit as x approaches -3 from the right of x. Even though this is a one-sided limit, remember we had a theorem that said if the two-sided limit exists, then each of the one-sided limits also equals the same thing. So since the limit as x approaches -3 of x will be -3, so will the one-sided limit. The following slide summarizes the rules for how to take limits of combinations of functions. So if I know that the limit of f and g exist, then I can combine them in the following ways and find their limits. So first off, let's look at the constant multiple rule. It says if I take any constant k and multiply it by f of x, and I want to know the limit of that, that's the same as if I first take the limit of f and then multiply it by k. The same kind of ideas throughout this. The sum rule says that if I want to take the limit of the function f plus g of x, that's the same as taking the limit of f plus the limit of g. The difference rule, limit of f minus g of x, is the same as limit of f minus the limit of g of x. So we can take these limits separately and then combine them by the operation rather than first combining the functions and then taking the limit. So we're kind of switching the order that we're looking at. So the product rule, if I take the limit of f times g, that's the same as first taking the limit of f and then multiplying by the limit of g. Before we go on to the next couple ones, I just again want to point out here that the first part of this says if these limits exist. So if these limits don't exist, that doesn't necessarily mean that the combinations don't exist. It just means that I can't use this theorem to do it. I can only use this theorem if I already know that the limits of f and g exist. So for the last two, there's a couple of constraints on them as well. So the quotient rule says that if I want to take the limit of the quotient f over g, that's the same as taking the limit of f and then dividing by the limit of g, as long as the limit of g doesn't equal 0, because you can't divide by 0. And again, because this is an if right here, I have the same kind of thing that if this limit equals 0, that doesn't necessarily mean that this limit of f over g doesn't exist. It just means I can't use this theorem to calculate the limit. We'll learn some other rules to calculate limits when I have a 0 in the denominator. The last rule is the power rule, which says if I take a function to a power k, where k is a rational number, and I want to find the limit of that, that's the same as first taking the limit of f of x and then taking that limit to the power of k. The extra constraint here is that when I take this value, the limit as x approaches c of f of x, and raise that to the k, that number has to be defined. So if my limit was, say, -1, then I can't look at this theorem with k equals 1/2 because then I'd be trying to take the square root of a negative number, which I can't do. So as long as you don't have anything like that happening, then you can use this rule, the power rule, to calculate your limits of a function to some power k. Let's do a couple more examples that apply these new limit rules that we've learned. In the first example, we're given that the limit as x approaches 0 of f of x equals -3, and that the limit as x approaches 0 of g of x equals 4, and we want to find the limit as x approaches 0 of the function 4 times f of x times the square root of g of x. So first, I can use the constant multiple rule to pull the 4 outside of the limit. So we end up with 4 times the limit as x approaches 0 of f of x times the square root of g of x. Next, I can use the product rule to separate the functions f and g. So I end up with 4 times the limit as x approaches 0 of f of x times the limit as x approaches 0 of the square root of g of x. Next, I can use the power rule on g of x. Since it's the square root of g of x, that's really g of x to the 1/2 power. The only thing that you have to watch out for here is that you aren't taking the square root of a negative number, but since the limit of g is +4, we can use this rule here. So we would end up with 4 times the limit as x approaches 0 of f of x times the square root of the limit as x approaches 0 of g of x. And now we can just plug in the values that we know. The limit as x approaches 0 of f of x was given to us as -3, and then the limit as x approaches 0 of g of x was 4. 4 times -3 is 12. The square root of 4 is 2, and then -12 times 2 is -24. So my final limit is -24. Next, we're going to see what happens when we take the limit of a polynomial. So here we've got the limit as x approaches 2 of the polynomial 4x cubed minus 6x plus 3. So first, I'm going to use the sum and difference rules to separate this based on the pluses and minuses. So now I'm going to have the limit as x approaches 2 of 4x cubed minus, using the difference rule, the limit as x approaches 2 of 6x plus the limit as x approaches 2 of 3. Next, I can use the constant multiple rule to pull the constants outside of the limits. So we'll have 4 times the limit as x approaches 2 of x cubed minus 6 times the limit as x approaches 2 of x plus the limit as x approaches 2 of 3. Lastly, I'm going to use the power rule on x cubed. So we'll end up with 4 times the limit as x approaches 2 of x, and then take that limit to the third power. The rest of this will stay the same, so let me just write it down again. And now we can use the rules that were listed on the first page of this video of taking the limits of very basic functions to evaluate this limit. So the limit as x approaches 2 of the function x is just 2, minus 6, the limit as x approaches 2 of x, as we just said, is 2, plus the limit as x approaches 2 of the constant 3 is the constant 3. And now we're just going to simplify, so 2 cubed is 8, times 4 is 32, 6 times 2 is 12, plus the 3, 32 minus 12 plus 3 is 23. Now recall that our original function that we were taking the limit of here was the polynomial 4x cubed minus 6x plus 3. Now, if we evaluate this function at 2, we get 4 times 2 cubed minus 6 times 2 plus 3, which is 23. So we're getting the same answer. And this is a property of polynomials, that if we're going to take the limit as x approaches a value of a polynomial, that limit is the same as if we just evaluated the function at that specific value. So normally we've been saying that the limit of a function is different from the value of the function at a specific point, but for polynomials this ends up being equal to each other. So that is the summary of limit rules and how to calculate some basic limits using more algebraic methods.